Well, I guess we can go ahead and get started. So let me welcome everybody to our 25th Fall Astronomy Day lecture, now known as the Joe Klein Memorial Lecture. We've had one year that we missed because of the pandemic, but we've been doing this since 1997, so we've got a long list of great speakers, and we have another one to add to the list tonight. For most of our history, this event's been held in Corey Auditorium on the Jamestown campus at GTCC, but as you see, we're virtual again this year, and we hope to be back in person in 2023. Also, the Klein Observatory is open every Friday night if the skies are clear, usually, but because of the logistics associated with tonight's event, with all our volunteers out at a variety of places watching the talk, we are taking this week off, so no observing after the talk tonight, but please come and join us on a future Friday so that you can come look through our telescopes. As I said, we're open every clear Friday night throughout the year, unless there's some special circumstance. These public viewings, the visiting speakers and other programs that we have throughout the year, they wouldn't be possible without the vision and support of, as always, Don and Joe Klein and Aaron and Ruth Martin and their family. They are the ones that spearheaded this effort, that started the first Fall Astronomy Day lecture that got our observatory built on campus, and we're thankful, as always, for what they've done for astronomy here in the Triad. And of course, we have support from the GTCC Foundation. They help us bring the speakers in, maintain our observatory, and stage our public viewings. And of course, we've got lots of volunteers who help us out on Friday nights. And I see several of them are watching tonight, and so thank you all for all the good work that you do to help bring astronomy to the people here in the Triad. Looking ahead, we're hoping to put together another virtual lecture potentially in November, and our TriStar and North Carolina Science Festival events, including the Stellar Society lecture, will be coming up in the spring in March and April. Hopefully those will be in person, but we'll see what happens. So check back at the Klein Observatory website or check us out on Twitter for updates as those dates approach. So now it's time to get the program underway for tonight's exoplanet talk. We're really excited to have Dr. Rebecca Dawson from Penn State University as our speaker tonight. She's the Penn State Astronomy and Astrophysics Schaffer Career Development Associate Professor of Astronomy and Associate Head for their graduate program. She received her BA in Astrophysics from Wellesley and a Ph.D. in Astronomy and Astrophysics from Harvard University. She was a Miller postdoctoral fellow at UC Berkeley. Her research interests include extrasolar planets, debris disks, dynamics of planetary and satellite systems, the Kuiper belt, planet formation, and signal processing. And her work has gained her many accolades. She's been awarded many of the early career prizes of the major societies in the field. The American Astronomical Society recognized her work with the Cannon Award and Warner Prize, and the AAS Division of Planetary Science awarded her the Harold Urey Prize. She's at the forefront in the field of study of exoplanet systems, and tonight she's going to share with us a little of what that research is telling us. If you have questions throughout the talk, let me mention that there's a chat feature where you can type those questions in, and we'll have some Q&A at the end of the talk. Let me turn things over now to Becky Dawson for tonight's presentation. Take it away, Becky.
Great, thank you so much. So glad to be able to join you all virtually. I'm excited to talk to you today about how the thousands of discovered extrasolar planets, planets orbiting other stars, or exoplanets as we call them, can serve as a window on the history and habitability of planetary systems. But let's start a little closer to home in our own solar system, at our own kitchen table, where you may have made a model like this of the solar system as a kid, or maybe your children have made something like this. and you had the sun, and then you put the rocky planets, Mercury, Venus, Earth, and Mars, close to the sun, and then the giant planets, Jupiter, Saturn, Uranus, and Neptune, further out. And this is how a solar system was supposed to look. But we know that our own solar system is orbiting a star, and that it's one of hundreds of millions of stars in the Milky Way. And this raises the question, what do their solar systems look like? Is ours the standard or something else?
Excuse me, Becky.
And
We're
yeah.
seeing just your first slide,
Oh, you're seeing
so
just my
somehow
first slide.
you're not in
Oh,
the right play mode.
okay. Just a moment. Let me try sharing my whole screen instead of just the slides. Maybe that will fix this. You're like, oh, her talk is a little monotonous. All right. Oh, that was not actually what I meant to do. Let's see. All right. All right. Do you see something else now? Okay.
Yes.
Let me show you. Here's your kitchen model of the solar system. And then here's our galaxy with its hundreds of millions of stars. And we are wondering, do they have their own solar systems? And do they look like ours? And when you go out and stargaze at night, we also ask the question, I wonder which of those stars have their own solar system and what they look like. So it's something that people have wondered about, I'm sure, for millions of years, or at least since the dawn of human history. But it's an exciting time where we're finally able to start answering that question. This is a graph showing the number of discovered planets over time, starting in the early 1990s. And it keeps growing and growing. We have this deluge of discoveries, and we now know of thousands of planets in other solar systems. We're starting to be able to answer that question, what do those solar systems look like? And the answer is they look very strange. So a lot of the planets that we found orbiting other stars look bizarrely different from anything that we have in the solar system. It's been quite surprising. I sometimes compare to working on extrasolar planets to a party, a space planet party. And it's a lot of fun, but it's not like the friendly little family birthday party depicted here. Instead, it's more like the party that you throw in high school when you send out an invitation and suddenly your parents are out of town, suddenly a bunch of unexpected guests show up. You have no idea who they are or what they're doing there. That's how it's felt to discover some of these really strange and exotic extrasolar planets that we'll talk more about in a moment. It's also like a party where we're still waiting for the guest of honor, that really Earth-like, Earth twin planet hasn't yet shown up, even though that's maybe who we're most excited to meet. So a lot of people are wondering how common are Earth-like planets, and are doing a lot of work to try to answer this question. And we sometimes call that how common are Earth-like planets eta Earth. That's the fraction of sun-like stars with an Earth-like planet. But despite headlines telling us every other day that we've found the most Earth-like planet ever, we still haven't found that real Earth twin. And we still have a lot of uncertainty about how common Earth-like planets are. So a recent study here at Penn State did what I think was the most careful job to try to answer that question and say, okay, what's the fraction of stars with Earth-like planets given the planets that we've detected so far, and to take into account all the different uncertainties, the planets that we missed, the ones that we can't detect. And they came to the conclusion that it's still uncertain. And at best, we can put something like a 0.3 Earth-like planets per star upper limit on how many stars have an Earth-like planet. And for sun-like stars, our estimate of this eta Earth is really based on extrapolation, because we haven't detected something just like the Earth yet, so we have to guess based on detecting planets that are somewhat like the Earth in certain ways. So it's not a really satisfactory answer to this question yet. So my talk is called Beyond Data Earth because I'm going to talk about, okay, we don't know exactly yet how common Earth-like planets are, but what we can learn from the planets that we have discovered is quite a lot. They can give us a window onto the history and habitability of planetary systems. And so we're going to, for now, put aside the very fascinating question of how common are Earth-like planets, and then instead ask the question, what do the thousands of confirmed extrasolar planets that we do know about tell us about the history and habitability of planetary systems? Our field is advancing towards finding an Earth-like planet and finding a planet where there's some sign of life, whether it's seeing signs of life in an atmosphere with the James Webb Space Telescope, or seeing a blue dot like our own through the direct imaging of the future. But when we find this maybe habitable planet, we're not going to want to study it in isolation. In our own solar system, understanding the whole system tells us a lot about the history and habitability of the Earth. For example, the Earth's spacing from Mars and Venus tell us about how it formed and when it formed. The orbits of the giant planets and objects out in the Kuiper Belt like Pluto tell us something about the early orbital evolution of the solar system. And compositions of asteroids and other small bodies tell us about how materials were moved around in the early solar system and how that might have affected the Earth's composition. So the next question we'll talk about today is, how can we best study future individual potentially habitable planets that are discovered in the context of their system? So let's start with the first question. What are the thousands of planets we do know about telling us about the history and habitability of planetary systems? So I mentioned that a lot of the planets that have been discovered looked very different from what we expected. So let's talk now about what did we expect based on our own solar system. So based on our solar system, we had this very simple picture of planet formation. Our textbook version of planet formation started with a cloud of gas and dust that was spinning, and as it collapsed, since it was spinning, it flattened into a disk. Then we thought that far away from the star, a lot of material is ice, frozen, and so there's a lot of solid stuff around that can go into a big solid core, and then that core can accrete a bunch of the gas from the disk, and then we get a gas giant. Then the thought was, after a few million years, the gas disk goes away, and then rocky planets like the Earth form on the inner solar system on a longer time scale. And this simple theory was really good at explaining our solar system, and in particular, a few key characteristics. First, that we have rocky planets close to our sun and giant planets further out, that our planets are mostly on circular orbits because of the gas disk keeping them nice and circular, and that they're all orbiting in the same plane as each other because they formed out of this disk. So then we started to wonder, let's test this out with some other solar systems. And so now we'll move on to, do they look like that? If not, what's going on? So I want to start by showing you a plot where planet size is on the vertical axis, orbital period is on the horizontal axis, and the longer the orbital period, the farther away the planet is from the star. And you can see our own solar system planets on here, just like in that little kitchen model. We have the rocky planets closer to our sun, we have the gas giants further out. And one thing that's interesting is that we don't really have any planets closer to the star than Mercury. But most of the planets discovered around other stars, because of what we're sensitive to, actually have orbital periods shorter than Mercury. So they're in this region of the solar system, of their own system, that's completely empty in the solar system. And as such, they give us a new window on the origins of planetary systems. So some of our first views through the window back when planets were first starting to be discovered around other stars were really just peeking through the blinds because the detection technique could only find the biggest planets. We called these planets close to this star hot and warm Jupiters, and we're quite astonished to see them there. So this is why we asked, who invited the hot Jupiter? Why are there these close and giant planets at our party? How does that happen in a solar system? In fact, a number of the first discovered extrasolar planets are very unexpected guests, giant planets in inner solar systems. We have hot Jupiters, which are planets that are orbiting 10 times closer to their star than Mercury to the sun, and yet they are giant planets. We have giant planets that have been found on highly elliptical orbits. So the Earth is on a very circular orbit. Its eccentricity is 0.02, but we have planets with much more extremely elliptical orbits. And even planets that instead of orbiting in the plane that their star is rotating, have very tilted orbits that are misaligned with their star spin. So when we go back to this theory, suddenly we're seeing that all the solar systems share these key characteristics. So what does that say about our theory of planet formation? It doesn't necessarily mean it's wrong, but there's something missing. So the question is, what physical processes are missing from this to give us the wide variety of planets that we actually know about now? So what if you're just really interested in Earth-like planets, why should you care that there's giant planets close to their star in some systems? Well, when I was in graduate school, saw a movie that gave a pretty good analogy for why we should care. It was the Hobbit movie. So in the Hobbit movie, we have the Hobbit is having all these rocks fall as he's climbing around on this mountain. And eventually he realizes it's not a mountain, it's a giant that's fighting with another giant. And that's why there are all these rocks falling around. And so in this analogy, the giant planets in the system would be like these giants, and the Hobbit would be like a small Earth-like planet. So if there's dramatic things going on with the giant planets in the system, that's going to affect the little Earth-like planets too. The giant planets are going to really dominate the system. So that motivates us to really try to understand what's going on with them, even if you really only care about the Earth-like planets. Another way that I like to think about it is these hot Jupiter planets, giant planets close to their star, they're not very common. Only about 1 in 100 stars has one, but they're probably an extreme outcome of processes that are happening in many planetary systems. And indeed, as we consider theories that lead to a hot Jupiter, we find that a lot of them usually don't make a hot Jupiter. It's just a very extreme case, but the same kind of thing is affecting even solar systems that don't have a hot Jupiter. So how do you get a giant planet close to its star? There's 3 sorts of scenarios that have been proposed for this. One possibility is that the giant planet might be able to form really close to its star, which is very different from how we thought planet formation worked before, but is a possibility people are exploring. Another possibility is that they form far out from their star like we thought, out where our own Jupiter does, and that while that disk is still around the star, the disk the planets are forming out of, that disk might push the planet in close to the star, which is called disk migration. The final possibility is a little more complicated. So we might have the Jupiter form far from its star, like our own Jupiter, and then after the disk disappears, something, maybe another planet in the system, disturbs it onto a very elliptical orbit, kind of like a comet where it comes in close to the star periodically. And when a Jupiter gets very close to its star, tides can start to shrink and circularize its orbit. and that's called tidal migration. So that's another way to get a Jupiter close to its star. And all three of these theories seem like a pretty plausible explanation for why you might get a hot Jupiter. So what are the implications of these ideas for the Earth-like planets in the system? So we're now going to see a movie, a computer simulation showing something dramatic happening to really shake up the planets in a system. And we're going to try to figure out what the consequences are for the Earth-like planets in the system. So let me show you what you're looking at here. So on your left, we have a star. To the right of the star is a system where some giant planets, which are black, have formed. And then this is before the rocky planets form, which happens later. And what we see now is some rocky material that the rocky planets are going to form out of. The separations are in terms of the Earth-Sun separation. So we can see our black giant planets are out near where our solar system giant planets are. And then there's a lot of material inside the giant planets that's going to be turned into small rocky planets, we hope. So let's see what happens here. We have the material that's close to the star that's going to turn into rocky planets. It's kind of colliding. Planets are starting to grow. It's getting a little shooken up by the giant planet's influence, but so far everything looks okay. We have planets forming close to the star, but watch, because something terrible is about to happen. Oh no! So now giant planets gravitationally disturbed each other, and you can see all that material that was supposed to be our Earth-like planets is gone. It either hit the giant planets or it got kicked out of the system. So when something dramatic happens to shake up the orbit of giant planets, it can be really bad for the Earth-like planets in the system. So this makes it sound like giant planets are really these bullies of their system, but they're less, I think there could be less like bullies and more like an older sibling who sometimes bosses you around, but also can stand up for you too. We can see that it kind of depends on which of these scenarios is operating, how much of an effect the giant planet is going to have, and whether it's going to be good or bad. So if we have a giant planet get disturbed onto this very elliptical orbit, like we saw in the movie, that could be really bad for the rocky planets that might form. But if instead we have a giant planet that's just quietly forming, or maybe just gently moving in through the disk, that might be okay for the rocky planets in the system. And in fact, it can be really good for them, just like the older sibling that protects you. We think that Jupiter in our solar system can protect us from comets and other things coming in from the outer solar system. So this is a time-lapse photo of comet Shoemaker-Levy hitting Jupiter. So we can think of Jupiter as kind of shielding us from a bunch of the stuff that's coming in from the outer solar system that might be bad for life if it were to hit us on the Earth. Another really helpful thing a giant planet can do is to bring us water from the outer solar system, which is of course vital to life here on Earth. The region where we think the Earth formed was really dry because it was a region where there wasn't a lot of ices. It wasn't cold enough for ice. So if our Earth just formed there undisturbed, it might end up really without much water, which would not be good for life. So now we're going to see how a giant planet can be a bit more benevolent on its effect. So let me walk you through this movie now. So we have on your left is the star. Then we have this planet forming material. And then on the right is the giant planet. And now we're going to pay attention to the color of the planet forming material. The red material close to the star is very dry. And then the material that's further out where there's more ices is a lot more watery. And if we look at one astronomical unit, that's like where the Earth is located, we can see it's very dry material, which is not so good. So we're now going to see, we just have this one giant planet sitting here, kind of jostling things around, how that can bring us more watery material to the Earth. So we can see materials getting a little shuffled around. Some of the stuff is moving in. And if you look at the color of stuff near 1, you can see it starts out red, so it's very dry. But over time, you're going to see it change to orange as it gets some more water brought in from further out. Now it's getting to be like a light yellow and green. And now it's like a blue color. So now the Earth has some water on it, which is very good for habitable conditions, we think. So in this case, the giant planet was quite helpful in getting water-rich material to the Earth. So depending on what's happening with the giant planets, if they're being very violent and disturbing each other and knocking away Earth-like planets, it can either be bad for habitability, or it might be good if a giant planet is just sitting there helping material come closer in. It's either a good or a bad thing to have a giant planet, depending on exactly what that giant planet is doing. So let's now revisit though, which of these things is actually happening in giant planet systems? All 3 of these can lead to a giant planet close to its star. So what's usually going on to get that close-in giant planet or that hot Jupiter? Well, one great thing is that although any of these 3 things can give us a hot Jupiter, we now know of hundreds of hot Jupiters, and we know a lot more about them. We don't just know that they're there close to their star, but we know other properties. And we can try to use some of those properties to test those 3 different theories. So some of the properties we can think about are what are properties of the star. That's the star is shown in yellow. So how old is the star? Does the star have a lot of metals in it, or is it just made of gas? What's its tilt? Is it on the same plane as the hot Jupiter or not? Then we could think about like physical properties of the Jupiter. How big is it? What's its atmosphere like? We can think of orbital properties. Is it on an elliptical orbit? How far is it from the star? How common are these hot Jupiters? And then we can also see, well, what else is in the system with the hot Jupiter? Are there planets nearby it? Are there planets further away? And we can compare what we know about these close-in giant planets, these hot Jupiters, to smaller planets that are close in, or to giant planets that are a bit further out, known as warm Jupiters. We can hope to use all of this information to help us distinguish which of those 3 theories is really responsible for hot Jupiters. So this looks complicated, but I'm going to walk you through what you need to know. We recently put together, well, a few years ago, this giant table of all the things that we know about hot Jupiters, or HJs as we call here. We know about their orbits and their sizes and their atmospheres and everything. And then we considered those 3 different theories that I talked about. They formed where we see them, they moved in gently through the disk, or they had that elliptical tidal migration. And then we see, is that theory consistent with the properties of the hot Jupiters? Check. Is it inconsistent? X. And then O and T means we're not really sure yet. And what I want you to take away from this table is that there's no column that has all check marks, and every column has some X's too. So what that means is that none of these 3 scenarios is totally explaining everything that we know about hot Jupiters. And that suggests that it's probably not just one cause, that there's probably multiple of these theories at work that are leading to hot Jupiters, and some hot Jupiters might form close to their star, some might come in through another mechanism. It's a mixture is what this is suggesting. So let's take a moment to look at some of these properties that led to this conclusion. The first one we'll talk about is the eccentricity, which is how elliptical the orbit is. And this is something that's important because we have this mechanism, this tidal migration, where the Jupiter starts out on a highly elliptical orbit and circularizes. So we might see signs of that if that's really the common type of origin for them. So this is one of the slightly more complicated plots of the talk, but I'm going to walk you through it. It's in 2 dimensions. So on the vertical axis, we have how elliptical is the planet's orbit. Bottom of the plot is very circular, top is extremely elliptical. And then on the horizontal axis, we have how far away is the Jupiter from its sun? Is it really close on your left, or is it pretty far away, which is on your right? Then what we have is, how do these different processes that we talked about move planets around on this plot? So we have in gray, what if planets are gravitationally disturbing each other? That can raise their eccentricities quite a lot. In blue is, what if the planet is being gently pushed around in the disk? That could move the planet a lot closer to the star, but it's going to keep the planet on a very circular orbit. And if the planet gets disturbed onto an orbit that's elliptical enough that it starts to get tidally stretched out, it can be in the red part of the plot, undergoing high eccentricity tidal migration. So if we see planets in the red portion of the plot, that's telling us they're undergoing this tidal migration theory that we talked about. The yellow parts of the plot are where a planet would hit the star or get tidally disrupted, so we don't expect to see any planets here. So this is our expectations, and now with these hundreds of Jupiters, we can put them on the plot and see where they lie. So here they are. Here are the observed Jupiters on the plot. We see they're all over the place. But when we look in the red region, which is where the tidal migration must be happening, we see that there's actually planets in there. And that's suggesting that at least some of the Jupiters are coming in through tidal migration. Another important property that we can bring in that I briefly mentioned is how many metals does the star have? Some stars are just hydrogen and helium, but others have metals like iron, oxygen, etc., that are in their atmospheres. So one very interesting early result from exoplanets is that stars that have more heavy elements are more likely to have a giant planet. If you have a star that's mostly just hydrogen and helium, it probably doesn't have a giant planet. But if it has lots of iron, oxygen, and metals in there, there's a much higher chance that it'll have a giant planet. That's an observed trend. And the interpretation of this has been, if you have the disk around the star is probably made out of the same material that the star is. If you have more metals, it's easier to make the core of a giant planet, and then it's easier for that planet to accrete gas. So having more metal in the star means more metal in the disk and maybe easier to make giant planets. So an interesting thing we found is that when you go back to this plot of how elliptical is the planet and where is it, and we look in this red region where I said these planets are undergoing tidal migration to get close to their star, we notice that most of these planets are orbiting the stars that have more heavy metals in them. Overall, there's more red points on this plot, more giant planets orbiting metal-rich star, but it's even more pronounced when we look at these planets that we think are experiencing tidal migration. They are like even more exclusively orbiting the metal-rich stars. And that's in contrast to, in the blue box are just close-in hot Jupiters that are on circular orbits. So they've either finished tidally circularizing, or maybe they come from one of those other channels, the disk migration or the in situ. And there we see some of them orbit stars with more heavy metals, but some orbit stars with fewer heavy metals. There's more of a mix, which is not what we'd expect if these circular ones are just the circular version of the elliptical ones. So that's suggesting that there's more than one contribution to the hot Jupiter population. And if we think about this story again, that has interesting implications for Earth-like planets. Maybe some of them have been disturbed by high eccentricities, but others have not. So the thought is that this high eccentricity migration mechanism is only happening around the higher metallicity star. Maybe that's because it needs other giant planets. We don't know for sure that other giant planets are what caused the eccentricity, but that's a good explanation. Like, that's what happened here. Giant planets disturbed each other. And if you have a disk with more metals, maybe you're more likely to form multiple giant planets, and that leads you to be able to disturb each other and have this tidal migration happen. Meanwhile, maybe the disk migration or in situ formation that would give us go straight to a circular hot Jupiter, maybe that can happen around either metal-rich or metal-poor stars. It doesn't need a bunch of giant planets, so it doesn't matter as much. And that's why we see there are some circular ones that are orbiting the less metal-rich stars. So another interesting property of these hot Jupiters that we can look at are the companions in the system. And in particular, do they have other planets nearby? We think that, just like we saw in that movie, that this high eccentricity tidal migration process would probably destroy any small planets there. So we expect, if this tidal migration is happening, that there shouldn't be other small planets nearby. Meanwhile, if we have the planet just forming where we see it or moving gently through the disk, we could have small planets form as well, and we might expect nearby planets. So what people have found when they have investigated this is that most of these hot Jupiters don't have nearby companions, in contrast to other planets where there are often a lot of them together. And that implies that tidal migration is likely at work. However, there are exceptions. For example, there's a system called WASP 47b, where there's a close-in giant planet and then two nearby small planets. So this probably didn't have tidal migration happen. That would have destroyed these little planets. It probably is the result of disk migration or in situ formation. So here's another piece of evidence that there's maybe multiple channels contributing to hot Jupiters if they don't all come in one way. So some takeaways from what we talked about of giant planets for habitable planets. Some giant planet systems we've talked about show evidence of an early upheaval that likely would have wiped out habitable planets. But others show evidence of a more gentle history, which is compatible to, or even helpful to, habitability. And this implies that both types of histories sculpt planetary system, and that planet formation conditions, in particular how many solids are available to make giant planets, might be a deciding factor. If you'd like to learn more about the origins of hot Jupiters, this month actually in Sky and Telescope, I wrote an article about hot Jupiters that's in that magazine. So if you're interested in learning more, check it out. All right, so now we're going to spend a little bit of time talking about smaller planets. So the first planets discovered were giant planets, mostly giant planets close to their stars. But with more recent surveys, we've started to become more sensitive to intermediate size and mass planets, which are sometimes called super-Earths because they're planets that are in between the size of Earth and Neptune. So we started to really raise the blind, be able to look at more of this close-in planet parameter space and open the window. And people were surprised but excited to find, not working, sorry about that, a real oasis of planets. Let me see if this is going to work. No. Okay. Hold on a second. All right, what I'm going to have to do is let me try something really quick. I'm going to pull up, I actually was just showing this plot in my class, so let me see if it appears on the class version or if it has the same. No, it's probably going to have the same issue. Just a moment. All right, we will look at this class version for a moment. So now we're really zooming in to close-in planets. We're looking at a plot of planet radius versus orbital period. Longer orbital periods are further out. And these are planets that were discovered by the Kepler mission, which is one of the surveys that was more sensitive to smaller planets. And what we can see is that there are tons of planets that are intermediate in size between Earth and Neptune, and on short orbital periods shorter than Mercury. Of course, it's partly that those are the planets that we're sensitive to, but when we try to correct for what planets we're sensitive to, we still find that intrinsically these planets are extremely common, maybe about anywhere between 20% to half of stars have a planet between the size of Earth and Neptune with an orbit closer to the star than Mercury, even though we have nothing like that in the solar system. All right, let me go back to my other plot. Okay, another puzzling thing about these intermediate sized planets that we're seeing around other stars is that they have, you might have been wondering, like, what are they made of? They're between the size of Earth and Neptune. Are they more like Earth? Are they more like Neptune? And it turns out they span a whole range of possibilities. Some of them seem more like scaled up Earths, and some of them seem more like scaled down Neptunes, which means they're rocky with a small gaseous envelope. And one way we can see this wide diversity in these planets is in this plot, which is showing how dense is the planet on the vertical axis, and then how big is the planet on the horizontal axis. And so when we look at planets that are between 1 Earth radii and 4 Earth radii, so that's Neptune size, between the size of Earth and Neptune, we find that they span this giant range of densities. There are some that are less dense than water, and some that are far more dense than rock. So there's this real variety in these planets. Then another really interesting thing is to look at their orbits. So the orbits of these close-in planets have surprised us a lot as well. And I like to compare them to something we see in the Kuiper Belt, a dynamically cold population. And let me explain what that means. What it means is that these close-in super-Earths are often very, very circular, even more circular than the planets in our solar system. They're very flat, all in the same plane, even flatter than in our solar system. And they're packed very tight together, even more tightly packed than our solar system rocky planets. So that was surprising because we thought we understood why our own solar system planets had the spacings they did, have the orbits and flatness that they do. And these ones are really defying our explanations by being so tightly packed and flat and circular. Another interesting trend that's emerged, what this is like a portrait of a bunch of different planetary systems. So each row is its own planetary system. And what you kind of notice as you look at them is some systems have a bunch of little planets, some have a bunch of larger planets, and the planets are kind of evenly spaced within a system. It's not that each planetary system has identical planets, but compared to the wide variety of planets overall, within a system, the planets are kind of similar to each other. So planets within the same system seem to have similar sizes and spacings to each other compared to the overall variety. So we have this surprise that instead of having rocky planets close to the star, gas giants further out, we have these kind of intermediate planets that are very close to the star. And they seem to be too flat and circular. We expected them to be kind of like our solar system, but instead they're ultra flat and nearly perfectly circular. Another thing about some of this very interesting about some of these close-in planetary systems is that those that are orbiting very cool stars might actually have habitable conditions. So this is showing a scale picture of, on the bottom is our solar system. And then if we look way inside at that little blue ring close to our star, that would be the TRAPPIST-1 system, a system discovered that has a bunch of planets very close to its star. But because that star is very cool, some of those planets might have habitable conditions. And there's also a scale showing Jupiter and its moons, Io, Ganymede, and Europa. So this planetary system looks more like Jupiter and its moons than like our solar system, and yet these planets might be habitable. So why do we care about these super Earths and mini Neptunes close to their star for formation and habitability? One is that they're very common. So they must be telling us about a common mode of planet formation, even though it's different than the solar system. Another thing is that, as I showed, they're very diverse. There's like a wide range of them, and that hints that there's maybe some diversity in the formation and evolution processes that may sculpt other systems too. So if we can really understand why they end up to be so different in different systems, we can really understand all the types of formation processes and conditions that are going on. Finally, some of them are orbiting red dwarfs or low mass stars. And even though they are very close to those stars, the stars are so cool that these planets might have habitable conditions. So what's going on? What's wrong with this picture that it doesn't give us a super Earth or mini Neptune in our solar system? Why are these planets so flat and circular? We're going to talk a little bit more about that now. So to understand why it's so surprising that we get these planets, we're going to go back to another cartoon to try to better understand why we expected to have rocky planets close to the star and gas giants further out to begin with. We just kind of mentioned that in this cartoon, but let's look at that a bit more. So we now have a cartoon where you have a star on the left, and then in green is the gas disk that we're looking at. So the inner disk is material that's very close to the star. The outer disk is material that's further away. And then over time, as you go down the cartoon, the gas disk is going away. So what we expected was that in the outer disk, we can form these much bigger cores because there's a lot of ices around. But in the inner disk, we can't, and we just have these very small planetary embryos until the gas goes away. So the idea is in the outer disk, those big cores can accrete gas and become gas giants. But in the inner disk, we have these just little mini cores, and they can't grow very much while there's still gas around because it's cushioning them from each other, and it has to wait around for the gas disk to go away, and then they can grow through giant impacts or hitting each other. And that's what we think happened in our solar system to make our own terrestrial planets. So can't see this plot, but what does it mean that there's so many planets, super Earths and mini Neptunes close to their star? Well, we had this idea that we had to wait around for the gas to go away to get these giant impacts. But what if we don't have to wait? What if it can happen a little bit early? So if we take the conditions close to the star and really dial up the amount of solids and say, what if there's quite a bit more solid material here than we thought? Then suddenly the solids can start to compete with the gas. And instead of having to wait for the gas to totally go away, they can start to have the giant impacts while there's still gas around. then they might be able to accrete a low mass atmosphere and end up as these mini Neptunes that we observe. So this can happen if there's enough solid material in the disk to let us form planets while there's still gas around. Okay, this was my concern, and it's so strange because we tested this out and I thought it was working then. Let's see what to do. If I can make this bigger. I don't think I can. Okay, well, what I will tell you is that we have done simulations of this process and indeed find that these super Earths and mini Neptunes can form if we have enough solid material available to work with. And this will let us grow planets just like in the cartoon that merge and grow through giant impacts and become super Earths and mini Neptunes. So why then do we have such a variety? Some of them are rocky, some of them aren't. So one possibility is that there's a whole range of conditions in the disk. Some of them might be more like our solar system and don't have many solids. And you have to wait for the gas to go away to grow the close-in planets. Others might have more solids and they get to form their planets while there's gas around. And that's why some systems have planets with small gas envelopes, the mini Neptunes, and some of them have super Earths. Another very interesting thing is that the gas can very much affect the orbits. If the planets form while there's still gas around, that can keep the planets very compact and circular and coplanar. We find in our simulations that they stay like that even over the long time scale of the system after the gas goes away. So because of this, we also expect we can get some very compact circular coplanar systems if we have the planets forming close to their star while there's still gas around. Meanwhile, in the systems like our solar system that have fewer solids available, where we have to wait around for the gas disk to go away, they get their orbits a little more disturbed. Nothing super dramatic, but just a little bit jostled like in our own solar system where the orbits aren't perfectly circular or perfectly coplanar. I think this is one of the last plots that you won't be able to see because there's mostly just cartoons. So when we look at this in our simulations, we can indeed find we get this wide range of planet compositions, and that the big factor controlling this is how much solid material is in the disk. Is it like the solar system with less solid material, or does it have a lot more solid material? And because of this, we expect two kind of modes of super Earth formation. One, where there's a lot of solids available to form planets close to the star. We get these very compact, circular, flat, tightly spaced orbits, and the planets end up as low-density mini-Neptunes. In other systems that are more like the solar system, there's fewer solids available to form planets close to the star, and we get rocky planets that are more elliptical, mutually inclined, and wider spaced. Again, nothing dramatic, but like our solar system where things aren't perfectly circular. So we think that rather than having this neat division that we did in our original cartoon, where first we have the gas disk and the gas giants form, and then we have the gas go away and the rocky planets form, there might be a lot going on in between where we have a little bit of gas left, and in some systems we can have these compact systems of low density planets form. And indeed, we find in our simulations that if we ignore the effects of this gas disk as it's going away, we end up with planets like the solar system that are more widely spaced and mutually inclined and elliptical. But if we include the effects of this gas disk, we can get these very compact coplanar circular planets. Oh, there is one more plot that you can't see. Okay. Hopefully you can see it a little bit on the bottom left. So the other thing that we find with these simulations is we also get systems that are very similar with the planets inside them. So within a system, the planets look like each other. They have similar spacings. And so what's controlling that here is the amount of solids available close to the star. With less solids, we get these smaller, a little more widely spaced planets. And with more, we get more larger planets, wider spacings. So this might be like a very important factor in controlling why planetary systems look so different from each other. So our takeaways, first, a range of formation conditions in the planetary disk, in particular, the reservoir of how much solid material is available to form close to the star, can contribute to the diversity. And we have analogs to our solar system forming in disks with fewer solids available in the terrestrial planet formation region. Another interesting implication is that close-in planets, including habitable ones, may have formed close to where we see them today. So this scenario that we looked at had the planets forming in place. They didn't form further away and migrate in. And so some of these close-in planets might just be locals. They're not something that formed far away and moved in. So in the last couple minutes, we're going to quickly touch on how can we best study individual potentially habitable planets in the context of their system. And we talked about in the beginning of the talk how important it was to understand the whole system to really understand the history and habitability of the Earth. So how do we start to do that for other systems? We have a big problem right now is that we have all these different techniques for finding planets, but most of them can only look at a very small piece of each system, maybe just at the planets really close to their stars or just at the faraway planets. And usually the different techniques are being used on different stars. So instead of having this nice, complete view of any individual system, we just have a bunch of fragmented views of other systems, and we don't know what the whole system looks like. And that's because the different types of detection techniques, which are shown as different colors here, look at different regions of the system. That's depicted here in that we have planet mass horizontally in orbital period, and you can see some of the techniques, like some of the colors are looking just at the close and massive planets, some are looking at planets further away, some are looking at the really far away planets, and it's all different systems, so we don't have this nice complete view of any single system except our solar system. Fortunately, there are missions happening right now and planned for the future that are going to help address this problem. So the TESS mission, which is a space telescope, is going to be looking at, well, is right now looking at very bright stars in the sky. And the cool thing about it is that these bright stars where it finds planets can be observed using other techniques as well. So we might have a situation where instead of just seeing part of a system, we can use all different techniques to find a more complete inventory of what's there. The Gaia space mission, which is going on right now, is going to detect planets that are a lot further from their stars, but it's looking at some of the same systems where we know about close-in planets already. So this is also going to fill in what is a whole complete view of a single system. Then finally, some of the next generation instruments are going to be more and more precise and let us find smaller and smaller planets in longer orbital periods. So those new instruments may be able to map out an entire system. Finally, we're going to get a really interesting dimension from James Webb Space Telescope, which recently launched. We're starting to get some of the new results because it's going to be able to characterize the planet atmosphere. So then we won't just know, okay, there's a planet there, we might know its mass. Instead, we will know what's actually in its atmosphere, which is very important. However, to really be able to map out another system like our solar system, we need to be able to do direct imaging, which is where we take a picture of the system to study the full system and the details of each planet in the system, what its atmosphere is like, and what kind of asteroid belts and so forth are in the system. The goal is to be able to take a picture of an Earth-like planet. And right now we can take pictures of very young giant planets very far from their star. And what we want is a telescope that can take a picture of an Earth twin. The cool thing is that if we make a telescope that's capable of that, we'll really be able to map out the whole system kind of for free, because the same type of telescope that can do that can really tell us all about the system. So this is a mock image where this is like, what if we could take a picture of the solar system from another star? On the right, we see our little Earth, and you can see how we can see all the planets in our solar system in this image, and we can start to see even effects of planets on the asteroid and Kuiper belt. So if we can take a picture of an Earth 2.0, we can also see everything else in the system if we make the right design choices for that telescope. So I'll end with this. This is where I've created a cartoon of an imaginary planetary system that we might be able to map out in the future with a giant space telescope, as is now being envisioned. In this imaginary planetary system, we have in green is like where planets might be habitable given their temperature. And in this imaginary system, we have like an inner asteroid belt. It's being shepherded or kept in place by the Earth-like planets in the system. And I'm imagining that we found that these systems are these planets are very water rich, maybe even more water rich than the Earth, and that they're in a special resonant configuration, and that together implies that they might have formed a little bit further out and moved in a bit. We also see a gap between an outer asteroid belt and one of the planets. That also strengthens this interpretation that maybe it moved in a little bit. We also see a very elliptical Jupiter in the system, but not so elliptical as to disturb the inner planets, and a debris ring that's a bit offset because of being disturbed by this elliptical Jupiter. And maybe this also helped with bringing in more water-rich material to the system. So again, this is totally imaginary, but this is what we hope to be able to do in the future. Have some other solar system that looks nothing like ours, but where we have this full view of the system so that we can really piece together what happened there as we have for our solar system. So we're envisioning a giant space telescope of the future that can do this. I worked on a mission concept called LUVOIR for the Decadal Survey. And this has ended up, which is what astronomers get together to choose the priority for the upcoming decades. And a telescope like this was a major priority that was selected. So hopefully in the future, we're going to have kind of a giant Hubble Space Telescope in space that can take a bunch of pictures of planetary systems and find Earth-like planets, and also help us understand it in the context of its whole system. So I'll leave you with a couple of takeaways. We need to characterize the entire system to understand the formation and habitability of planets in the context of their solar systems. And current techniques and precisions limit our window onto each system. So we need giant telescopes for a full view. To conclude, as we answer our original questions, so what do the thousands of confirmed extrasolar planets tell us about the history and habitability of planetary systems? They're telling us that there's a diversity of formation and evolution conditions. Not every system evolves the same way, and only some are compatible with habitability. And how can we best study future individual, potentially habitable planets in the context of their system? We want to get a full view of each system like we have from the solar system, And we can envision doing that with future direct imaging, maybe with a giant space telescope. So I'll leave you with this summary, and thank you very much.
Thank you. Thank you very much. That was great. So the chat is open for questions if people have them. I'll start now while people are typing in. You mentioned when you were talking about the inner solar system processes, you talked about more solids versus fewer solids in the disk. Is that just a function of metallicity, or are you talking about other processes populating that area with solid materials?
Yeah, that's a great question. So it probably needs to be material from further out coming in. And one of the reasons for that is the amount of material that we need there is so much that it wouldn't really match any overall metallicity that we see for host stars. It's a lot more. And in fact, if we take that amount of solids and kind of scale up the gas accordingly, astronomers have found that such a disk wouldn't even be stable because it would be just so massive. So we think that it probably needs to be, rather than like a disk that has tons of solid overall, a disk where it's very effectively brought in solids from further out and concentrated them close in so that they can form into planets that way. But there still might be at least a correlation with having a more metal-rich star, and it's a little bit debatable in the data, but there are hints that, yeah, these mini Neptunes are more common around the metal-rich stars as well, just like the giant planets.
So the aperture of such a space telescope that you advocated for at the end, how big an instrument are we talking about?
Yeah, so for the study we did, we looked at two sizes, 9-meter and 15-meter, so really big. Another team looked at, I think, like a 6 and an 8-meter, like a somewhat smaller version. And the decadal survey that decided this is a big priority didn't make a final decision on exactly how big it should be. So a lot bigger than Hubble. The bigger the better, like the bigger the more Earth-like planets we're going to be able to see. So we have to decide whether we want to invest in getting tons of Earth-like planets or whether we'll be satisfied with a smaller number and not have to build such a giant telescope. And of course, for some of the other science applications, there's the same trade-off, the bigger the better, but it's also just very challenging and expensive to make such a big telescope. So that's going to have to be decided at a later point, like exactly how big we're talking about. But even 6 meters would be really big compared to Hubble. So still really big.
You mentioned that some of the planets are orbiting small red dwarf stars such that they may be in the habitable zone. Can you speak to the stability, variability of these stars? Are they potentially too unstable to have a close habitable zone?
Yeah, so one of the big concerns that people have about these low mass stars as hosts of habitable planets is that, so all stars when they're young are a lot more active, they're putting out a lot more high energy radiation, but for these low mass stars, that stage lasts a lot longer, and having a lot of high energy radiation from these stars might be very damaging to life. So people have concerns that might not make these the best place to look for life. That being said, we know on the Earth that life finds a way in really extreme conditions, so people also don't want to rule it out for that reason. And there might be older stars where things have really calmed down. So there's still debate about whether these low mass stars even if they have planets with the right temperature, would actually be able to host life. But I think there's enough uncertainty that people still think it's quite interesting and worth looking for.
So here's one. How would hot Jupiters form in situ close to the star when the classical model requires giant planet formation to happen beyond the ice line?
Yeah, so the reason the classic model needed it to form beyond the ice line was that we thought in order to have enough solids to go into the core, we need to have all the icy material. Like we need lots of solids, so we need to be somewhere where there's ices around as well. However, we now know about all these super Earths and mini Neptunes that are really close to the star. So if you can form that kind of planet close to the star, then it's like, what's stopping you from forming a Jupiter there as well? If we, for example, need to have a lot of materials get close to the star to go into these super Earths and mini Neptunes, if it happens early enough, maybe it can actually become a hot Jupiter as like an extreme case. So that's the thinking there, that I think finding all these close-in super Earths and mini Neptunes, which pretty much seem like the core of a giant planet, so common, has really made people think, okay, if those planets are there, maybe they also migrated in, but if not, maybe if they form there, what's to stop you from going a little step further and making a giant planet?
Is a certain stellar class like G, K, etc., more stable, and therefore more suited to long-term habitable planet development?
Yeah, in terms of stellar, yeah. So some people have thought that maybe stars called K dwarfs, so those are somewhere in between a very low mass red dwarf and a sun-like star, might be kind of the sweet spot because they're lower mass and cooler, so you can have habitable planets closer in, easier to detect, but they're not as active with all the high energy radiation as the lower mass stars. So maybe those are kind of the best possible ones. But there's not really a super strong argument that those are the best. Like, why not a sun-like star? Or maybe it's not so bad with the low mass red dwarfs. So there's not such a favorite that like no one's even bothering to look at anything else. But some people do think maybe the sweet spot is these kind of intermediate stars.
Is the discovery of so many exoplanets doing anything for the debate of the definition of a planet?
Yeah, good question. So,
Oh, and we see
so
the glare on
far,
your head now, so tilt
oh,
your
nice.
screen again.
So far, the planets that we are sensitive to, are able to detect, like very clearly meet the criteria that's been now laid out by the International Astronomical Unit for a planet, except with one actually very interesting exception. So if you look at the actual criteria, it says to be a planet, you must orbit the sun. It doesn't say a star, it says the sun. And none of these planets orbit the sun. So if you're going to be super strict about it, then maybe none of them are planets. But I think that's more just the definition needs to be tweaked a bit. But there aren't really any that are violating any of the other criteria. So I don't think it's really motivated anyone to try to revise that definition. Maybe the exception being, like, I think part of what made the IAU adopt such a strict definition, the International Astronomical Unit, was there's this thought that we have to draw the line somewhere. We can't have hundreds of planets in our solar system, so let's be very strict about it, even though we now exclude Pluto. But if we know of so many planets in other solar systems, maybe it wouldn't be so bad to have a bunch in our solar system too. So that might make people not want to be so strict about the criteria for being a planet. So I think To summarize, I don't think anyone's like seriously thought of revising it because of the discovery of extrasolar planets, but there are a couple uncomfortable things about the current definition.
Will we be able to observe potentially habitable satellites of planets or satellites at all?
Yeah, there have been a lot of interest in hunts for satellites or moons of planets, and there have even been a couple like very tentative detections that really aren't strong enough to be for even the authors to be fully confident in, but it's a very active area where people are really thinking about how do we detect these moons around planets, and do we see any signs of them in the data? And indeed, there could be a moon that's like, if you think of, say, a giant planet at Earth separation, the giant planet's probably not going to have habitable conditions, but if it has a moon, maybe the moon has habitable conditions. So that really expands the possibilities. But so far, it's been challenging to detect these moons, and there's not yet been a definitive detection.
Any planets observed in binary systems, and how would a binary system affect the type of work that you do?
Yeah. So there's a lot of planets that are known to be in binary star systems. I assume this is about binary stars rather than binary planets. Okay. So some of them are, there's like a close in two stars very orbiting very close to each other, and then the planet is orbiting around both of them. And some, the planet's orbiting around one star, and then there's another star that's a lot further out orbiting. So there's been a lot of systems discovered like this, and um, it kind of it, for a lot of configurations, there wouldn't be a very noticeable effect on what we talked about today, because like if you consider a binary star that's very far away, it's probably not having a huge effect on the inner system. But there can be important effects, like having a binary star may help tilt the disk that the planet formed out of, and that might be an explanation for why some of these planets are on these very tilted orbits. It can, if you have planets orbiting a pair of binary stars, then where you can actually form planets is going to be a bit different, like where they actually can have stable orbits. So it definitely can affect planet properties, and individual systems might limit where you form planets, but it doesn't dramatically change anything that we talked about today. And we see that in the types of planets that are observed, that they're often fairly similar to those in single star systems, with some possible small distinctions in properties.
And now that you mention it, what about binary planets? Have we detected any such thing?
Yeah, we haven't detected a binary planet, like two similar mass planets orbiting each other, or in the discussion with students today, we talked about like two planets sharing the same orbit. So in principle, these things can exist, like they can have stable orbits, but they haven't been, no such planets have been detected so far.
Has this field of study had any significant impact on the estimates of the Drake equation?
Yeah, so the Drake equation is an equation calculating like how common do we expect other civilizations to be, and there's all these different factors that go into it. But A to Earth, how common are Earth-like planets? That's an important factor in there. Like if most stars don't have an Earth-like planet, that makes it less likely that there'd be other civilizations. So I think, so what we talked about today, in terms of well, in terms of the actual estimate of eta Earth, it's quite important, but also in terms of how other planets in the system are affecting the habitability. Like if we had found like, oh yes, pretty much all other giant planets go really unstable and destroy their Earth-like planets, then that would imply fewer civilizations. So to the extent that any impact on habitability is going to ultimately affect how likely are we to have another civilization.
And I don't know if everybody knows, we recently lost Frank Drake. He died of several weeks ago, a few weeks ago. So I remember he was the first astronomer I ever saw give a lecture here in the Triad back in the 70s, I think. Since super
That's really
Earths
cool.
are,
I used to have a T-shirt with the Drake equation that was signed by Frank Drake,
wow,
and it's really too bad that I don't have it anymore. I don't know what happened to it, but uh, that was
very
quite
cool.
fun to get that T-shirt signed.
Um, since super Earths are common to find, does that mean all our rocky planets in our solar system that are smaller means that they're outliers and are rare to find?
Yeah, that's a great question. So not necessarily. We know less about the smaller planets just because they're harder to detect. And they may be just as common or even more common than super Earths. So we know that these super Earths and mini Neptunes are very common, but we don't. That doesn't mean that Earth-like planets aren't also or even more common. That's kind of we're still figuring out. One thing we do know is that giant planets like our Jupiter and Saturn aren't really that common. Only about 10% of stars have one. So we're actually in the minority for having one of those.
Okay, if we had some kind of extraterrestrial contact with an alien civilization, what kinds of questions would you ask them about their own solar system? Is there anything we could learn by getting them to share their observations of the sun and our solar system?
Oh, that's interesting. Um, so I guess I can't immediately think of like something we could learn about our solar system from a distance that we couldn't learn up close. But I would certainly want to ask them all about their solar system because there's so much we can learn only from sending a spacecraft to a planet or from visiting it. Um, if we were observing our own solar system, we would know so very little about Venus or Jupiter or Saturn. We really had, or Pluto, we really had to send spacecraft there to figure out what was going on. So that we would have a lot of, we'd want to know all the details about the planets in the solar system that we can't really tell without sending something there. But I'll have to think if they would know something about our solar system that we don't know. I can't immediately think of something, but maybe if I think about it more, there is.
Could you sort of match what they see and can infer versus what we know, and then flip that over to what we see and can infer about them? Maybe that'll tell you something about how you interpret what you see looking at other systems.
Yeah, I mean, that's certainly the case. Like, they might say, oh, we thought Venus was probably the habitable planet in the system. You live on Earth? That surprises us. I guess one thing that's a little bit like this, but not exactly, is that here at Penn State, there's a group that's been observing the sun with the same instruments as we observe other stars to look for planets to try to better understand how spots and other things going on in the sun might interfere with detecting the planets. Because we know from like observatories that are looking at the sun exactly what's going on, so we can see, okay, these are the details of going on, but this is what we'd see in the instrument, and then we can kind of use that to understand when we look at another star what really might be going on given what we can see with our um, rough instrument, and we can't actually like trace spots across that star and so forth.
Is there a single extrasolar system that we seem to have a full understanding or inventory of, or that we can
Uh,
say we're close to?
no, I feel that there really isn't. I mean, there are some solar systems, for example, um, there's a directly image system called HR 8799 where we know a lot about it. Like we know about debris belts there, we know about planets, we know about some of their atmospheres, but we really don't know anything interior to, I think, about 10 astronomical units because we can only look at the outer part of that system. So there are systems where we're starting to learn quite a lot, but I don't think, I would say that there's not a system where we have a complete picture of it yet, besides their solar system.
So it looks like I've exhausted the questions and we've been at it a while. So let me just draw the line on that. And thank you again for a wonderful talk and for your time tonight. So let's everybody thank Dr. Dawson. You can do your little clap hands icons. Um, and thank you all for coming out tonight. And thanks especially to Leanna Martin for helping us run the show tonight as well behind the scenes. Um, and come out and see us on a Friday night. Monitor our website for other events coming up. And thanks everybody for coming.